Welcome to this video. In this video, I will be talking about the phase estimation problem. So we are given a state psi. Let me change the color. So we are given a state psi and a unitary gate u, and the promise is that the state is the eigenvector of the unitary operator, and the eigenvalue can be written in this particular form, which has modulus 1. And now the question is to determine what is the value of theta. So theta lies between 0 and 1. So theta lies between 0 and 1, and the question is to determine its value. So when theta is 0, we know that this is basically 0 eigenvalue, and when theta is very close to 1, then also we know that the eigenvalue is 0. So now we will also work for the special case, and we can think of this as a promise or a restriction in our approximation of theta, that we will take theta to be of the form of alpha over 2 power m, and alpha is a integer between 0 to 2 power m minus 1. So for example, if m is 1, then theta takes this particular value, 0 or half, and if m is 2, then theta can be 0, 1 by 4, half, 3 by 4, like this. So because alpha, so in this case alpha can be 0, 1, 2, 3, and this case alpha is 0, 1. And now we will the question is, what is theta we have to determine. That's the question, and the idea is theta will always be of this form, particular form that I just said. So you can see that if m is very large, for example m equal to 100, then these values will become very this value will be very close, and it will almost nicely look like a real line which is discretized in this particular fashion. So in this case we will first start with analyzing of kickback of powers of u. So this is the first case we will analyze. This will be one of the important circuits, that important part of a circuit that will come into play. So you have 0, you have a Hadamard gate, and then you have a controlled action of u power n. So you have this as the control, and then you have a state psi. So what is the state in the output is the question, and this is easy to see. The idea is that if the state is 0, nothing happens, but if the state is 1, then u power n gets applied to psi, which gives us e power 2 pi I theta n as the phase in front of psi. So this can be written in a concise fashion as this particular line here. So you have O output, you have psi output as 1 over root 2. This is just the factor coming due to the Hadamard gate, and then you have summation over a belonging to 0 and 1, and then e power 2 pi I a theta times n acting on a psi times a psi, not acting on, this is just a number. So this is the phase kickback that I am denoting here. So this is different from the phase kickback we saw for Deutsch-Dojda algorithm or the Grover search algorithm. But this is also kind of a phase kickback. You have, if you have power n, you have n times the kickback, and A is nicely taking care of the fact that if it is 0, then nothing happens. If it is 1, then you conditionally apply the unitary gates. So now we will look at the special case, which is called basically 2 qubit phase estimation problem. And for m equal to 2, theta belongs to 0, 1 by 4, 2 by 4, 3 by 4. This is for example promised, right? So we have to determine what is the theta basically. So here we have the circuit. We have two ancillas, two zero qubits, and Hadamard gate, and we have the unitary which will give the phase kickback. So we can collect the phase kickbacks in together. So I have 2 pi I have a single phase kickback, and I have a 2 times the phase kickback, because you saw here the n was appearing a number of times. So I have this as the phase kickback, and then I have the basis states and state psi. So this is the action of the entire circuit, and now I have written something as QFT4 dagger, which I will discuss in a moment. But now let's just analyze this particular term, which is the output 1. So for this, consider a0, a1 as integers. So basically a0 is a variable that takes 0 or 1, a1 is a variable that takes 0 or 1, and you are summing over all of them. So you can think about 0 0 as being the 0 integer, 1 0 being 1 integer, 0 1 as being 2, and 1 1 as being 3. So this can be thought about as a binary representation of the integers x. So you can write x as a0 plus 2 times a1, which is exactly the kickback phase factor that we have. So this means what we can do is we can write psi 1 as this particular term here, where now I have replaced the binary digits 0 and 1 with the integers as per this convention. So this is the convention. Now what we can do is from here we write theta as y by 4. So because we know that m equal to 2, that's the case we are working. So theta is of the form of y by 4, where y belongs to 0 1 2 3. So once we write that, we get this particular line here. So we have this here, and now this is said to be a quantum Fourier transform operation. So this is what I have written, QFT4, 4, I will say what it stands for, and it is acting on y and tensor psi. So now what is quantum Fourier transform operation? So QFTN acting on a state y, which can be written as phi of y. So I have enumerated y in this way. It is 1 over root n, you have a prefactor. Then you have sum of x equal to 0 to n minus 1, the basis elements, and then you have omega x times y, and omega n is basically 2 e power 2 pi I over n, this factor. So this is simply a operation which is a unitary operation. So to see this, one just have to prove that any two columns of this matrix that I can form is orthogonal to each other. So and each column is also normalized, we have to prove. So let's try to prove that. So as matrix it look like this. You have omega xy n, omega n xy, then you have xy. And now the claim is it is a unitary operation. So QFTN is a unitary operation is the claim. So for this you can take two different columns, z and y, or y and z, and if y is equal to z, then you can see that this term becomes 1, and you are summing over it n times, so you get 1. Now if y is not equal to z, then this is like a geometric series sum, where the basically the in the geometric series the multiple that we have, so you have a square, a cube. So this a is of the form of omega n y minus z. So you have the sum as a power n minus 1 over a minus 1. But omega power n times y minus z, this will be 1, because omega is this particular e power 2 pi I over n. So this is 0 basically. So what we have shown is the columns of the matrix are orthonormal, and so this matrix is a unitary transformation. It changes a basis set to another basis set. So now the output of psi 1, so the output of circuit 1, which is psi 1, so let's come back here. So this is 1. It can be written as quantum Fourier transform on 4 dimension acting on Y tensor psi, and using QFT4 inverse, which is the dagger because it is unitary, we get the final state as Y tensor psi. Now the computational basis measurement, what you can do is you can just measure Y in the computational basis to determine what the value is, and theta is simply Y by 4. So one thing to note is that when you do the computational basis measurement, you will get a bunch of zeros and ones. So this is the binary representation of Y. So this is the binary representation. So now we can generalize this circuit to talk about any phase estimation problem. So suppose we have m qubits, so m of these, and the idea is theta is of the form of y over 2 power m, such that y goes from 0, 1 up till 2 power m minus 1. Then you have these many integers that you want to code in the binary form. So this can be done by taking m qubits and then applying the controlled unitary operation in this particular fashion. So the first qubit gets a u, the second one gets a u square, and the mth one will get u power 2 power m minus 1. So if it is u, if m is 3, then 3 minus 1 is 2, so it is u power 4 for the third one. So why this 2 power m minus 1 is coming, one can think about using the binary representation. So if you want to encode 2 power m minus 1 integers in binary, you have to use starting from a0 to a1 to square a2 up till 2 power m minus 1 a m minus 1. So you need this form of number. So you need this as the kickback. So you need this as the kickback. This means the last unitary which will give a kick should be coming from this power. This is where the idea of the kickback of n unitaries comes into play. And now what this means is that you can write these as digits in the form of digits using the binary encoding, and you will get omega 2 power m xy. And once you have come up till here, you know that this is nothing but quantum Fourier transform of 2 power m. And now you can invert this quantum Fourier transform using the inverse, which is also a unitary operation, to get y tensor psi. And now you can measure each of the qubits. So this measurement, it is on each qubit, and you can measure each qubit to get the value of y in terms of binary form, and you can decode it to integer form, and then theta will be y over 2m. So that's all for this video. In this video we talked about kind of a specialization or specific case of this phase estimation problem. You can relax the promise that theta is of this form also, but I will not go into details of that. So that's all for this video.